In section point 5.2, we talked about probability distributions. They're usually given to us as tables, where in the left-hand column we have all possible outcomes, and in the right-hand column we have the probability associated with each of those outcomes. We said that in order to be a probability distribution, each one of the probabilities had to be a number between 0 and 1, which is basically just the definition of probability. And all of the probabilities had to add up either to 1 or something very, very close to 1, such as 0.999 or 1.001. In sections 5.3 and 5.4, we talk about a specific type of probability distribution known as a binomial probability distribution. We'll talk about the definition of a binomial probability distribution and how to find the mean, the variance, and the standard deviation of a binomial probability distribution. Binomial probability distributions have outcomes that fall into two categories. We can call the two categories success and failure, or acceptable and defective, or survived and died. When there are only two possible outcomes, there's a good chance that you're dealing with a binomial probability distribution. It does have other requirements, though. In order to be a binomial probability distribution, there has to be a fixed number of trials. You can say, I'm going to roll a die 10 times, and that's a fixed number of trial, but you can't say, I'm going to roll the die until I get a 7. The trials must be independent. What happens on one trial can in no way affect what's happening on another trial. Each trial must have all outcomes classified in two categories. We commonly just call those success and failure, but that's not a value judgment. Success is whatever we're studying. So if we're studying the number of people who develop a certain type of cancer, then developing that type of cancer would be what we were calling success, and not developing it would be a failure. It's very important to understand we're not saying that success is the good outcome and failure is the bad outcome. The fourth requirement is that the probability of success has to remain the same in all trials. It doesn't change from trial to trial. Examples of experiments which would be binomial experiments are tossing a coin 20 times to see how many tails occur. We definitely have a fixed number of trials. The trials are independent in that whatever the coin lands on in the first trial doesn't affect what the coin's going to land on in the second trial. Um, the experiment has two possible outcomes, heads and tails, and the probability of landing on tails is going to stay the same no matter how many times you flip the coin. So that's a binomial experiment. Asking 200 people if they watch ABC News, again, that's a fixed number of trials. Whether the first person watches ABC News doesn't affect whether the second person watches ABC News. And the two possible outcomes there are yes and no. The last example of a binomial experiment is rolling a die to see if a 5 appears. Well, there's a fixed number of trials there. We're only going to roll the die one time. There's only two possible outcomes, either yes, 5 appears, or no, 5 doesn't appear. Perhaps this is not the most useful example because we really can't talk about two events being independent if we're only rolling the die one time. But this does technically meet the criteria for being a binomial experiment. Examples which are not binomial experiments: rolling a die until a 6 appears. We don't know how long that's going to take. That's not a fixed number of trials. Asking 20 people how old they are. There are not only two outcomes to that question. Drawing 2 coins out of a bag of 20 coins and recording whether or not it's a nickel. If we phrase the question, is it a nickel, yes or no, then there are only two possible outcomes, but the events are not dependent. If I take one nickel out of the bag, it affects how many nickels are left in the bag for the next trial. So the two events are not independent, and that's not a binomial experiment. How about these examples? Number 6, treating an 863 subjects with Lipitor and asking each subject, how does your head feel? Well, we definitely have a fixed number of trials, but there's more than two possible outcomes to that. So it's not a binomial probability distribution because there's aren't just two outcomes. Number 8, treating 152 couples with the Y-sort gender selection method developed by the Genetics and IVF Institute and recording the gender of each of the 152 babies that are born. Certainly, there's a fixed number of trials. The gender of the first baby in no way affects the gender of the second baby, so the trials are independent. The probability of a girl or a boy is going to remain the same for all 152 births, and there are only two possible outcomes, male and female. So that is an example of a probability distribution, excuse me, a binomial probability distribution. Number 10, 15 governors are randomly selected from the 50 governors currently in office, and the gender of each governor is recorded. Well, there's a fixed number of trials. There are only two possible outcomes, um, male and female. And my first instinct says that the gender of Alaska's governor in no way affects the gender of Montana's governor. So, yes, they're independent, but we need to think carefully about this. What if I reworded it? There are 50 marbles in a bag, and we're going to draw out 15. Then would you consider the trials being independent? Let's say the 50 marbles were all either pink or blue, and we're going to draw out 15. Well, if we draw out a first pink marble, that's going to affect how many pink marbles are left. So we're not saying that the gender of Alaska's governor in any way causes the gender of Montana's governor to be a certain thing. But if you think of this as marbles in a bag, um, we're selecting without replacement. There's a certain number of these 50 governors currently in office. There's a fixed number of pink ones and a fixed number of blue ones. So if we're sampling these 15 without replacement, those events are not independent, and therefore it can't be a binomial distribution. Number 12, 200 statistics students are randomly selected, and each is asked if he or she owns a TI-84 Plus calculator. That's a fixed number of trials, 200, out of the entire population of statistics students, and there are thousands of statistics students across the country and across the world. We're going to select 200 and ask each one if he or she owns a TI-84. Well, there are only two possible outcomes to that, and whether one statistic student owns a calculator doesn't affect whether the next student's going to own a calculator. So yes, that is a binomial probability distribution. Let me say one other thing about number 10 and number 12. The 5% guideline tells us if we're drawing out less than 5% of the population, we can play like the events are independent. I didn't think of saying this at first, but number 10, we're drawing 15 out of 50. That's way more than 5%. So we can't use the cumbersome guideline or the guideline for cumbersome calculations and say we're just going to play like those events are independent. That is another reason that this answer is no, it's not a binomial distribution. But 200 statistics out of the entire population of statistics students definitely would be less than 5% of the population. And that's why we can consider those draws independent, and that is a binomial probability distribution. All right, the notation that you need to associate with binomial probability distributions. Whatever we're studying, that's what we're going to call success, and we're going to use capital S for the event of success and capital F for the event of failure. Little p and little q will denote the probabilities of S and F respectively. So little p is the probability of success, little q is the probability of failure. And since there are only two possible outcomes, success and failure, if you give me p, then I can find q. If you tell me the probability of drawing out a pink marble is zero point 0.7, then the probability of not drawing out a pink marble is zero point 0.3. Just subtract the probability of success from 1, and that will give you the probability of failure. Other notation that's very important in order for you to either use the formula for calculating mean of a binomial probability distribution or to calculate it on the calculator, you have to understand what these variables stand for. N is the fixed number of trials. X is a specific number of successes in N trials. I may say, what's the probability of 5 out of 13 girls in 13 births? What's the probability of 5 of them being girls? In that case, 13 is the number of trials, and 5 is the number of successes. X has to be a whole number. You can't have a partial success, and it has to be between 0 and n. If I have 13 births, then the fewest girls I can have is 0, and the most girls that I can have is 13. So X is always a whole number between 0 and n. P is the probability of success, Q is the probability of failure, and P of X is the probability of getting exactly X successes among N trials. Be sure that X and P both refer to the same category, being called a success. If success is drawing a pink marble out of a bag, then P has to be the probability of drawing a pink marble out of the bag. Or if S is, if we're studying again cancer patients and we say that X is the number of patients who have cancer, then P has to be the probability of drawing a patient with cancer. So make sure you clearly associate both X and P with whatever you've called success. And then here again is the guideline for cumbersome calculations. When sampling without replacement, consider the events to be independent if the sample size is less than 5% of the population. So even in events that are technically not independent, as long as our sample size is less than 5% of the population, we can pretend or assume that the events are independent. All right, how about this formula for binomial probability calculations? That is an interesting formula, and just let me mention to you, well, two things. Number one, we're not going to use the formula. I'm going to show you how to find the formula or find this value on the calculator. But also, just in case you're wondering what that exclamation mark is, N with an exclamation mark doesn't mean N in a really loud voice. That's called N factorial. And for example, if I had 5 factorial, that would mean to multiply 5 times 4 times 3 times 2 times 1. 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. All right. I just wanted to show you that formula so that you would truly appreciate your TI 83 and 84 and what it can do for you. It can find the probability of X successes faster than you can even read that formula. And again, what you'll need to substitute into the calculator, what you'll need to enter is the N, which is number of trials, the X, which is your number of successes, and the P, the probability of success in any one trial. If you give the calculator this P value, it can calculate the Q value that it needs for the formula. So how do we do this on a TI 83 or 84? To find the probability of X successes in N trials, where each success has a probability of P. Very important that you understand those variables. X is a number of successes, N is a number of trials, P is a probability of success. Choose second and VAERS. Right above your VAERS button on the calculator, it says DISTR, and that stands for distribution. We're going to talk about several kinds of distributions, but because distribution is in yellow above the VAERS key, to access it, I have to press second and then VAERS. Maybe I should turn it on first. Second and VAERS. And then I want to scroll down until I see binomial PDF. Right there it was. On my calculator, it's 0, binomial PDF. Now there's also binomial CDF, and we'll talk about it in a minute, but right now we want binomial PDF. So I'm going to choose that. On the operating system that's on my calculator, when I choose binomial PDF, it immediately goes to a blank screen, opens a parentheses, and waits on me to enter 3 values. The 3 values that I need to enter are the value of N and the value of P and the value of X. On some calculators, rather than going to this blank screen that says binomial PDF, you'll go to a screen that has binomial PDF at the top, and then it asks you for number of trials, number of successes, and probability of success. If that's how your calculator operates, you just enter those 3 numbers. For me, I'll need to enter the N and the P and the X separated by commas. One thing that will help you remember in what order to type in the 3 variables that you have to enter, you enter them in alphabetical order, the N and then the P and then the X, and press enter. Now, let me say this about the homework and specifically the view example and help me solve this tools in MyLabs Plus. From here on out, we're going to be using the calculator for almost everything that we do in statistics. But those help tools in MyMathLab are going to refer to formulas and tables in the back of the book. That will mess you up. Disregard if you use help me solve this or view example in MyLabs Plus, you only need to use it to make sure that you're getting the right values for N, P, and X. You can do that. But once they start plugging those values into this formula, you need to close the window, get out of help me solve this or view example, because we're not ever going to use that formula, and we're not ever going to use, well, one exception to that, and I'll tell you when we get there, but there's only one of those tables in the back of the book that we're going to use. So when MyLabs Plus shows you from the table in the back of the book, just close it. All right, let's see how this works. The brand name of McDonald's has a 95% recognition rate. Now, I don't know if that's in the US or in the world. Certainly, at least in the US, 95% of the people you ask would say, yes, I know what McDonald's is. It may even be the world. I don't know. If a McDonald's executive wants to verify that rate by beginning with a small sample of 15 randomly selected consumers, find the probability that exactly 13 out of 15 consumers recognize the McDonald's name brand. All right, remember what these variables stand for. N is the number of trials, or the sample size in this case. We're talking about 15 people in the sample. I'm sorry, I can't get that to mute, but it will stop ringing in just a second. There's 15 people in the sample. The probability of success, we're told, is 95%. I want to verify that the probability of someone knowing the name brand McDonald's is 0.95. And I want the probability that exactly 13 out of 15 do recognize that name. So X is 13. I'm going to pull up binomial PDF and enter the three variables in that order, n, then p, then x, 15, comma, 0.95, comma, 13. And I get that that probability rounded to 3 decimal places is 0.135. Now think about this a second. That's supposed to be the probability that 13 out of 15 consumers recognize McDonald's name brand. Um, if there's a 95% recognition rate, I would have thought that the probability of 13 out of 15 going, sure, I know what McDonald's is, I would have expected that probability to be much higher. Why is it so low? There's only a less than 14% chance that 13 out of 15 will be the number who recognize McDonald's brand name. The reason that probability is so low is because it's much more likely that either 14 or 15 will recognize the name brand. If there's a 95% recognition rate, then you would expect more than this 13 to go, yes, I know what McDonald's is. What about the second statement here? Find the probability that the number who recognize the brand name is not 13. Well, this is the probability that the number who recognizes the brand is 13. Not 13 is the complement of that. So to find the complement of the probability for 13, you could just say 1 minus 0.135 or 0.865 is the probability that the number who recognized the name brand is not 13. Let me put just a couple of other problems down here at the bottom. What about the probability that 14 out of 15 recognize the name brand McDonald's? To get the probability of 14 out of 15, I would enter binomial PDF out of 15 people, each having a probability of 0.95 for recognizing the name brand of McDonald's. What's the probability that exactly 14 of them do? I pulled up binomial PDF, 15, comma, 0.95, comma, 14, and found that probability to be higher, 0.366. And then I think I have room to squeeze one more example here. What about the probability of 15 out of 15? There's a 95% recognition rate. What's the probability that all 15 people go, yes, I know what McDonald's is? I'd enter that as binomial PDF 15.95, 15. And I got that probability to be 0.463. So there's almost a 50% chance that all 15 people will say, yes, I know what McDonald's is. Or if we add these two probabilities together, we get about a 0.8, no, 0.3, 0.83, 83% chance that either 14 or 15 will say, yes, I know what McDonald's is. All right. I need to stop this video. I need to go teach another class, and then we'll call this one part one. I will come back and take part two in a little bit. So you may need a break as well. Go ahead and take it, and we'll pick back up on the next slide, which is cumulative probabilities from binomial distributions.